During the 6th century BC, an influential and charismatic leader emerged, captivating the attention of a growing number of followers. He founded a cult around him, and he was seen as God or the Son of God by his followers. And according to legends, he had a golden thigh, he could be in two places at once, and so on. The group seems to have followed very eccentric or weird rituals and practices. For instance, prospective members who wanted to join the group had to complete a stringent 5-year period of silence. And by silence, I mean literal silence. During this period, they were only allowed to listen to the teachings of the leader behind a curtain, and this served as a test of commitment and dedication. Central to their philosophy was the belief in metempsychosis or reincarnation, as they believed that the soul transcends death and moves from one body to another. While historical accounts vary, it is believed that the group was one of the first vegetarians. It is also believed that they avoided beans, particularly fava beans, as they believed that the souls of the dead resided within them, and consequently they strictly refrained from consuming or even coming into contact with beans. One story surrounding the death of the leader tells that a son of a nobleman wanted to join the group, and when he got rejected, he formed a mob of people to destroy the group. The founder and leader of the group was running from the mob. That's when he encountered a field of fava beans. At that moment, he had two choices. He could either run over the field, compromising his belief but saving his life, or he could surrender and get himself killed by the mob. He chose to surrender and was ultimately killed by the mob. Now, you might be thinking that this must have been just some religious cult, but the founder and leader of this group was none other than Pythagoras, the man who you may remember for his famous theorem, the Pythagorean Theorem. And the Pythagorean Theorem alone had a very important role in the development of trigonometry, Euclidean geometry, and many more. But Pythagoras is also claimed to have made several key contributions to music, astronomy, and philosophy. Pythagoras and his followers had a huge influence on scientists and philosophers who came later. People like Plato, Johannes Kepler, Isaac Newton, and many other great scientists and thinkers revered Pythagoras' thinking. In fact, Isaac Newton gave credit for his discovery of universal law of gravitation to Pythagoras. But the thing about Pythagoras is that we have no concrete proof that the man even existed, let alone if he made any of the discoveries he is claimed to have made. And this is because the man never wrote anything, and some of the sources about him came several hundred years after his death. However, we can be sure that the group he formed, the Pythagorean Brotherhood, did exist. And we also know that numbers played a very important role in the philosophy of this group. The members did not treat numbers as merely tools that can help humans in various tasks. Instead, numbers were sort of divine to them. They were not researchers in the field of mathematics in the conventional sense. They believed that numbers were at the very foundation of reality, and the universe is made up of these pure rational numbers and mathematical patterns. And they almost worship numbers. Consequently, they made very fundamental discoveries in the field of mathematics and science later. And it is entirely possible that some of Pythagoras' claimed discoveries may have actually been the work of the members of his group. And this is totally fine for us, because our goal in this video is to get to know and appreciate the group's philosophy on numbers in the context of their claimed discoveries, learn why they were so revolutionary for its time, and what can we, modern humans, learn from them and apply in our own study of mathematics, science, and just life in general. Now, a funny thing about Pythagoras' theorem is that Babylonians, Egyptians, Indians, and Chinese may have known about the theorem before Pythagoras was even born. In fact, we have found an ancient Babylonian clay tablet that uses the theorem to find the diagonal of a rectangle, which serves as evidence that Babylonians knew about the theorem before Pythagoras. But the Pythagorean Brotherhood did a good job of popularizing it and giving it Pythagoras' name, and it is worth studying it. So almost all of us are familiar with the theorem. The square of the hypotenuse is equals to the sum of the squares of the sides. Pretty simple. But Greek mathematicians did not think in terms of mere symbols and numbers. They dealt with real physical things in mathematics. So what does it actually mean when we say a number squared? Now, if we have a line with length 3 units and we square this line, what we do is we extend this line into the second dimension like this and form a square with all sides equal. Now this square right here contains 9 1 unit by 1 unit squares, which by the way is also the area of this square. This is actually the reason why 3 squared is equals to 9 and why we say squared when we multiply a number by itself. So to get a real understanding of Pythagoras and all the other ancient Greek mathematicians' approach to maths, instead of thinking in terms of mere numbers like this, try thinking in terms of actual squares drawn along the sides of this right triangle. So according to the theorem, the number of 1 unit by 1 unit squares in both of these squares, 9 plus 16, is equal to the number of 1 unit by 1 unit squares, 25, in this square drawn along the hypotenuse of this right triangle. Now this instantly feels much more intuitive to work with. This certainly feels much more real. And this is exactly how you should think when studying mathematics. Now, how do we even know this is true? So for the proof of the Pythagorean theorem, there are hundreds of them available. People have proved the theorem in different ways. In fact, more than 350 of them. But I personally prefer a visual proof. So here we have 4 equal triangles, 4 equal right triangles with sides A, B and C, C being the hypotenuse. And we also have a square over here. So now I'm going to arrange these triangles on this square in a way that they form an inner square. So as we can see that this arrangement has formed an inner new smaller square, and the length of the side of the bigger square is A plus B. And since we know that the hypotenuse of all these triangles is same with length C, the area of this inner square has to be equal to C square. And now I'm going to rearrange these triangles in a new configuration. So as we can see that this configuration has formed 2 new smaller squares, and since the length of the side of the bigger square is A plus B, the length of this side has to be equal to B, and from this triangle over here we find the height of the square is also B. So the area of this square has to be equal to B square, and with the same logic applied to the other square over here, we find the area of this square has to be equal to A square. And now if I bring back our original square with triangles, we can see that the area occupied by the triangles has not really changed, and so the area of this blue part has to be equal to the area of the blue part over here. So A square plus B square has to be equal to C square. I mean, look at this. Can you imagine how obvious this certainly feels? We already knew this relationship, we take it for granted. But think of those ancient Greek mathematicians. This would have felt like magic to them. And no matter the size of the square and triangles, this relationship stays true. If you live in ancient times, mathematical patterns like these can feel like divine. Humankind has always tried to find meaning and order in the universe, and now you can imagine why the Pythagorean Brotherhood would have worshipped numbers. These pure patterns and numbers would have felt like something from the god or god themselves. This obsession with numbers led Pythagoras to make key discoveries in other fields as well. According to legends, Pythagoras was passing through a blacksmith shop when he heard the sound of hammers hitting metal. He observed that the pitch of the sound was dependent on the weight of the hammer. He also observed that when 2 hammers of certain weights were struck simultaneously, they produce a pleasant sound, while hammers of other weights did not. He then experimented with strings and found that when the length of 2 strings have simple integer ratios, they produce a pleasant sound when struck simultaneously. So when the lengths of 2 strings are in the ratio of 1:2, they produce a pleasant sound or an octave is produced. Other pleasant sounds are produced when the lengths of the strings are in the ratio of 3:2, called a fifth, and 4:3, called a fourth. These ratios form the basis of our music theory and are still very much used in our modern music. This discovery would have further led Pythagoras to believe that the world was made up of these ratios of numbers and mathematical patterns. If something as simple as sound obeys these ratios, then maybe everything in the universe obeys these ratios. Pythagoreans believed that the world was made up of these rational numbers. Rational numbers are those that can be expressed as a ratio of integers. For example, 1.5 as 3/2, 1.33 as 4/3, and so on. Now, everything was going well for Pythagoreans. They were finding these rational numbers and patterns everywhere and unlocking the mysteries of the universe. There was no imperfection in numbers. I mean, all numbers can be expressed as a ratio of integers, right? Enters Hippasus, one of the members of this Pythagorean Brotherhood. He was the one who actually proved the existence of irrational numbers, numbers that are neither rational nor integers. And there is an interesting story around this. It is believed that when Hippasus proved the existence of irrational numbers, it was so against the philosophy and belief of Pythagoreans that he was drowned at sea as a punishment. So the problem began like this. If we have a right triangle with sides other than the hypotenuse as 1 unit, then according to the Pythagorean theorem, x squared will be equal to 2. Then x will be equal to square root of 2. So what does square root of 2 represent? Well, it obviously represents the length of the hypotenuse. Now, what is the length of the hypotenuse in decimal? Well, we can try to measure the length with more and more precision, but we can't seem to end somewhere. We can always measure with more accuracy. We can see that the length is a decimal with a fractional component that does not seem to terminate. It keeps on going and it is non-repeating. And we can't express square root of 2 as a ratio of integers if it does not terminate and does not repeat. So is there a way to find out if square root of 2 is actually rational or not? But before we begin, you should know that any number multiplied by 2 gives an even number. An even number multiplied by an even number also gives an even number. And an odd number multiplied by an odd number gives an odd number. Well, Hippasus was extremely clever. He started his proof by assuming that square root of 2 is rational. That means we can express square root of 2 as a ratio of a over b, where a and b are some integers. And we also assume that the ratio of a over b is in the simplest form, meaning that a and b do not share a common factor other than 1. Then we multiply both the sides of the equation by b and square both the sides. Then we get 2 times b squared equals to a squared. Now we already know that 2 times any integer gives an even number, so a squared has to be even. And we also know that an even number times an even number gives an even number, so a has to be even as well. Now we can express a as 2 times x, where x is some integer. Then we replace a in the previous equation by 2 times x and get b squared equals to 2 times x squared. Now with the same logic applied, b squared and b has to be even as well. But we have a problem here now. We started our proof by assuming that a and b do not share a common factor other than 1. But we now know that a and b are even, so they obviously share 2 as a common factor. That means our initial assumption was wrong and square root of 2 is not rational. It is actually irrational. This is actually called proof by contradiction. So Pythagoreans obviously did not like it when things didn't agree with their beliefs, even when they could clearly see the proofs presented to them. The number 10 was the holiest of all numbers. It is believed that Pythagoreans would meet in groups not exceeding 10 members. They believed that the cosmos consists of only 10 celestial bodies, irrespective of what they observed. So ideas like these definitely sound a little crazy. But it was this passion for purity of numbers that led to a lot of breakthroughs as well. Pythagoras is also believed to be the first to claim that the earth was spherical, and he most likely came to this conclusion not through empirical evidences and experiments, but intuition and hunches. Maybe he observed that if the moon was round, then earth must also be round, and sphere was also considered a perfect shape in ancient Greece. So perhaps that touch of mysticism, that unwavering faith in a particular concept or idea of existence, which might appear absurd to others, may actually be the driving force that propels us towards uncharted territories of knowledge and liberate us from the shackles of conventional norm. We humans often associate science with the notion that only what is observable and measurable constitutes the ultimate truth. However, it is necessary to acknowledge that there may be realms of knowledge and understanding that extend beyond the boundaries of our empirical observations. Embracing a broader perspective that acknowledges the potential for unseen forces or concepts can open doors to new discoveries and insights that otherwise may remain inaccessible.